Right guys, we're nearly there with chapter 22, so we're on thermochemistry still. And the first thing we're going to look at is we are going to look at bond energy. So we said in the beginning, energy is needed to break bonds and it's released when bonds are formed. So energy is absorbed to break bonds and energy is released when new bonds are formed. So bond energy simply is the energy involved in breaking bonds. So the definition for it is here. It's the average energy required to break 1 mole of a particular covalent bond and to separate the neutral atoms completely from each other. So what that means, if you have 1 mole of methane here, the bond energy is the average energy required to separate the 4 atoms of hydrogen from the carbon. The reason it's talking about average energy here is because it might be easier or harder depending. So it might be easy to break this first bond and then it might be harder to break the second bond. So the first bond is being broken from CH4, the second bond is being broken from a CH3 ion. So it could be slightly different. So we're taking average energy values. A list of average energy values is given here. So the delta H, the heat of a reaction, is dependent on the amount of energy needed to break bonds and the amount of energy released when new bonds are formed. So the overall delta H takes into account how much bond energy is required and then how much of that energy is released again when new bonds are formed. And when we're forming bonds, this is going on to the last part of the chapter, it's heat of formation. And the heat of formation of a compound is the heat change that takes place when 1 mole of a compound in its standard state is formed from its elements in their standard state. So let's just break that down for a second. Standard state, that means the form that an element or compound takes at 25 degrees Celsius and 101 kilopascals pressure, so atmospheric pressure there. So we know that water, H2O, at room temperature, that's kind of what 25 degrees is, at normal atmospheric pressure is a liquid. So water is a liquid at 25 degrees Celsius. So we've got an L here. We know oxygen, gas, is in the air. And so that must mean that at that temperature and that pressure, oxygen is a gas. Hydrogen, we're being told here, is also a gas at that temperature. So that's what the little state symbols here are telling you. So if we saw an equation like this, same equation, but it's giving us H2O with a G, stating that H2O is a gas, that is not a heat of formation equation. So this value is not the heat of formation of water because it's forming water in a state that it's not its standard state. Similarly, the other key thing to note here is that it's when 1 mole of a compound is formed. So 1 mole of water is formed here. So this is the heat of formation of water. This is not the heat of formation of water because, as you can see, this is forming 2 moles of water. So again, like we've seen with heat of neutralization as well, you have to be talking about 1 mole here. So just a couple of notes to point out on this. Delta H values, so heat of formation values here are mostly negative. So again, that means it's exothermic, heat is being produced. Compounds are, the reason for this is that compounds are generally more stable than the elements that form them. The heat of formation of any element in its standard state is 0. So if we want to make an element in its standard state, so if we go back up here, if we wanted to make oxygen in its standard state, that heat of formation is going to be 0 because oxygen already exists as O2 gas in its standard state. So obviously to make that, no energy is required, no energy change will take place. And just to point out again in relation to them, you always rewrite the equations so that you only have 1 mole of product. So this equation is perfectly fine here, we can use that, but what we have to do is we have to rewrite it and divide everything by 2 so that we get 1 mole of our product over here. That's the key thing. And obviously if you're dividing by 2 in your equation, that means you're dividing your delta H value by 2 as well. And if you throw into your calculator 571.6 divided by 2, we should hopefully get a value around there. Last thing, so we're going into calculations based on heats of formation. And the law we're going to talk about now is basically an extension of the law of conservation of energy that you will see in physics and you'll have all seen in junior cycle. So the simple law of conservation of energy is that energy cannot be created or destroyed. It can only be converted from one form of energy into another. So a simple example here is you're inputting a certain amount of energy into a light bulb through electricity. And what you're getting from that is your useful energy output is your light energy. That's what we want from the light bulb. You also have some waste. You have some heat energy being produced. The light bulb is going to heat up. And so the total amount of light energy plus the total amount of heat energy produced is equal to the amount of electrical energy that was put in. So you're not losing energy, it's just being converted into different forms. And so we're going to use that principle to look at Hess's law. And Hess's law states that if a chemical reaction takes place in a number of stages, the sum of the heat changes in the separate stages is equal to the heat change if the reaction is carried out in one stage. So just to try to explain that in, another way, I've got a little map here of the journey from Dunmanway over to Bandon. And what Hess's law is saying, obviously I'm going to talk about distance here, and we'll convert it back to talking about energy in a second. So if I was to get in my car and travel from Dunmanway to Bandon, I'm going to travel this distance. It's probably around, is it 30 kilometers? I'm not sure, I should have checked that. Let's pretend it's 30 kilometers, I could be way off. I'm going to travel 30 kilometers along this road. If I decide, if my phone rings and I decide to pull in around Manch and take a phone call, and then get back in my car and drive along again all the way over to Bandon, I'm still going to travel the same distance. It doesn't matter that I took a slightly different approach to it. If I stopped and took a phone call in Manch and I decided then that I wanted to stop in Inniskeen and get a cup of coffee, I could stop there, get back in my car afterwards and head on over to Bandon. And it doesn't matter that I've made 2 stops along the way. By the time I get to my final destination in Bandon, I've travelled the same distance. And that's what Hess's law is telling us in terms of energy. So if I want to go from A to D here, that total, if I do that all at once, go from A straight to D, I'm going to use this, I'm going to produce a certain amount of energy. I'll have a certain delta H value. The other way I could do that, instead of doing it in one stage, I might decide that I can do it in broken down stages. I can first go from A to B, then I can go from B to C, and then from C I can go to D. So I'm still starting with the same reactant, I'm still ending up with the same product. I've just taken a different approach to how I got there. So my delta H value from going from A to D is the same as the difference from going A to B, then B to C, then C to D. So my one-step approach going from A to D, that delta H value is going to be the same as all of these delta H values added up. That's what this red equation here is telling us. So just to put that into perspective, we've got an example here. So I've got carbon and I want to convert it into carbon dioxide. There's 2 ways that I can do this. I can add in 1 mole of oxygen, and if they react completely together, which we'll assume that they will, I can do it in one step. I can go straight from carbon plus oxygen gives me carbon dioxide. The other way I could do this is by only adding in half a mole of oxygen first. And that way I'm going to take a little detour. I'm going to end up going from carbon plus the half mole of oxygen to carbon monoxide. And then I can choose to add in more oxygen, and that will convert carbon monoxide to carbon dioxide. So what we're saying here is I can do it in a one-step approach, or I can take two different steps. So it's the same as saying with your homework, if I give you two questions for homework, some of you might choose to sit down and do both of them one after the other straight away. Others of you might decide to do one tonight and one tomorrow night. But what you'll end up with, you'll both have started off with two questions to do. You'll both end up with two questions done at the end, but you've just taken different approaches. So here what we're saying is the delta H value for the one-step reaction is going to be equal to the delta H values of the two other reactions added together. So that's written out here. Delta H1, heat of formation 1, is equal to delta H2 plus delta H3. And you can see the question here is asking us to find this value. And so we've gone through that process here calling delta H2 X. We've rearranged and we've subbed in our values, rearranged to find X, which is equal to minus 111 kilojoules per mole. And so this reaction here, carbon plus half a mole of oxygen produces carbon dioxide, and the energy change there, the heat of formation, is minus 111 kilojoules per mole. So in the next video that you're going to go on to now, I'm going to go through the two types of calculation questions you can be asked on this course. One of them is like this, one of them is slightly different.